Matrix is a two-dimensional array organized by rows and columns. Visually speaking, you can think of a matrix as a table filled with numbers. For example, the iris dataset can be viewed as a data matrix. Each row in the dataset represents one iris flower sample. The first four columns are its features: sepal length, sepal width, petal length, and petal width. The final column shows its species. Using matrices as tables suggests the beginning. Their real power lies in linear transformations. We'll dive deeper into linear transformations in future videos. As we mentioned before, a row vector is a matrix with one row and multiple columns, while a column vector has multiple rows and just one column. A square matrix is one where the number of rows equals the number of columns. If a matrix A has shape M by P, that means it has M rows and P columns. For example, this black and white image of an iris flower becomes a 2990 by 2714 matrix. It means it has almost like 3000 rows and almost like 3000 columns, where each entry represents the grayscale value of a pixel. We can use I to represent the row index of a matrix A. I increases from top to bottom, ranging from 1 to m. We can write the first row of matrix A as row vector A superscript 1, the second row as superscript 2, and so on and so forth. In this sense, a matrix can be seen as an ordered collection of row vectors. Now let's use K to represent the column index. K increases from left to right, ranging from 1 to p. We can write the first column of matrix A as column vector A subscript 1, and the second column as column vector A subscript 2, and so on. Similarly, you can view a matrix as an ordered collection of column vectors. The entry in row I and column K of matrix A is written as A subscript IK. For example, the entry in the first row and the first column is A11, and the entry in the second row, third column is A23. Every matrix has a special set of elements called main diagonal entries. They're the ones where the row and column indices are equal. The line connecting these elements are known as the main diagonal. Imagine each matrix entry as a square cell of equal size. Then the main diagonal is a 45-degree line stretching from the top left corner down to the bottom right. No matter the shape of the matrix, tall, thin, short and wide, square, row, or column vector, the main diagonal always exists. Adding two matrices, A and B, of the same shape, meaning adding their elements position by position. Scalar multiplication means multiplying every entry in the matrix by the same number. Simply put, the transpose of a matrix is what you get when you swap its rows and columns. Transposing a matrix is one of the simplest yet most important operations in linear algebra. It is something people often get wrong, so it's worth creating a video to understand it better. You start with an M times P matrix A. Its transpose is P times N matrix. The elements on the main diagonal stay in the same place when you transpose. That is because each of these elements lies where the row index equals the column index. If you imagine each matrix entry as a square, transposing is like reflecting the matrix across its main diagonal. If you think of the matrix as a table, then transposing is just flipping the rows and columns. Now suppose you write matrix A as a collection of column vectors. Then transposing means turning each of those column vectors into corresponding row vectors. For example, the first column of matrix A becomes the first row of A transpose, and the second column becomes the second row, and so on. Likewise, if you think of the matrix in terms of row vectors, transposing turns each row vector into a column vector. For example, the first row of matrix A becomes the first column of A transpose. The second row becomes the second column, and so on. As we mentioned in an earlier video, transposing a column vector gives you a row vector, and transposing a row vector gives you a column vector. If a matrix is tall, meaning more rows than columns, its transpose will be white, and if it starts white, the transpose becomes tall. When you transpose a square matrix, it stays square, but the elements reflect across the main diagonal. And for symmetric matrices, the transpose is exactly the same as the original. The shape of the matrix may change when you transpose, but the rule stays the same. Rows becomes columns, columns become rows, and all relative positions stay intact. From geometric perspective, suppose A is a 3 times 2 matrix. Its row vectors can be seen as 3 arrows in the plane, and its column vectors as 2 arrows in 3-dimensional space. After transposing, matrix A transpose has 2 row vectors in 3D space, and 3 column vectors in the plane. Be careful, transpose is different from reflection. Transposing is specifically about switching rows with columns. Also, the main diagonal isn't just any diagonal. Matrix transpose is not a diagonal reflection, and transpose is not a left-right flip nor a top-bottom flip. Matrices have a rich variety of shapes, and each shape has its own unique purpose. As we mentioned before, a row vector can be seen as a matrix with 1 row, multiple columns, while a column vector is a matrix with 1 column and multiple rows. Any point on a plane can be written as a 2-dimensional column vector. A point in 3-dimensional space can be written as a 3-dimensional column vector. In RGB space, a color vector can also be expressed as a column vector. In a data matrix, column vectors are often used to store data for a single feature. For example, in the iris dataset, each column vector represents 1 feature, like sepal length, sepal width, petal length, or petal width. In data analysis, row vectors are typically used to represent individual samples in the dataset. In iris dataset, each row corresponds to a record of 1 iris flower and can be written as a row vector. A rectangular matrix is simply a matrix where the number of rows and columns are not equal. For example, a tall matrix is one where the number of rows is much greater than the number of columns. Visually, it looks like a tall pillar. For instance, the iris dataset is a tall matrix. Tall matrices are often used to represent datasets where the number of samples is much larger than the number of features. Meanwhile, a wide matrix is the opposite. The number of columns is much greater than the number of rows. If you transpose a tall matrix, you get a wide matrix, vice versa. A square matrix has the same number of rows and columns. Many operations in linear algebra like determinants, inverses, eigenvalue decompositions, are defined specifically for square matrices. If the transpose of a square matrix equals itself, then the matrix is called symmetric. In a symmetric matrix, the elements are mirror symmetric with respect to the main diagonal. In the diagonal matrix, all non-zero entries are on the main diagonal, and all off-diagonal elements must be zero. Diagonal matrices come in two types: diagonal square matrices and diagonal rectangular matrices. An identity matrix is a special kind of diagonal square matrix where all the diagonal entries are 1 and everything else is 0. Very soon we'll see the identity matrix appear in matrix multiplication, inverses, and orthonormal bases. Triangular matrices are another special type of square matrix. If all the entries below the main diagonal are 0, it is called an upper triangular matrix. If all the entries above the main diagonal are 0, it's called a lower triangular matrix. The transpose of an upper triangular matrix is a lower triangular matrix, and the other way around. If you're not quite satisfied with the shape of your matrix, you can actually chop it into smaller pieces. We can slice a big matrix into several smaller ones, almost like cutting tofu. Each small matrix is called a block or submatrix. For example, if you slice the matrix on the screen horizontally, matrix A gets divided into two submatrices. The block on the top is a diagonal square matrix, and the block below is a zero matrix. Matrix multiplication somehow combines two matrices to produce a new matrix. This video introduces the rules of matrix multiplication. Given how important matrix multiplication is, we'll also understand it from different perspectives: geometrical, from inner product, outer product, linear combination. We'll talk about them in the coming videos. Let's say now we have two matrices, A and B. Matrix A has a shape of M times P, meaning it has M rows and P columns. Matrix B has a shape P times N, meaning it has P rows and N columns. The product of A and B, denoted as AB or A at B, will be a matrix of shape M times N. From the perspective of shape matching, matrix multiplication AB requires that the number of columns in A equals the number of rows in B. Otherwise, multiplication cannot be performed. In the product AB, the number of rows come from A, the number of columns come from B. The matching dimension P effectively cancels out. A very good way to remember this is M times P at P times N, the middle dimension P is cancelled. Now let's see how to actually compute each entry of the matrix C, which is the product of A and B. The ij entry of C, called Cij, is the sum of the products of corresponding elements between the f row of A and the jth column of B. You might notice that row vector A at or times column vector B is itself some kind of matrix multiplication. A row vector A of shape 1 times P times a column vector B of shape P times 1 gives 1 times 1 matrix. And a 1 times 1 matrix is really just a single number, a scalar. So simply put, row vector A times column vector B is simply a vector inner product. That means computing A times B involves performing m times n inner products, one for each entry. Now let's talk about a very simple example. Matrix A has shape 2 times 3, matrix B has shape 3 times 2. So the result A times B gives us a shape 2 times 2. Looking at the shapes, in 2 times 3 adds 3 times 2. The 3 in the middle gets cancelled, leaving 2 times 2. Now let's compute each element of A times B. Firstly, let's compute the element in the first row and the first column of AB. Next, let's compute the element in the first row and the second column. Then compute the element in the second row, first column. Finally, compute the element in the second row and second column. One important thing to remember is that matrix multiplication is generally not commutative. On one hand, even if A times B makes sense, follows the multiplication rules, it doesn't mean B times A will also be valid. Even though sometimes B times A also is defined, it doesn't mean that A times B and B times A will give us the same result. For example, in our case earlier, B times A will produce a 3 times 3 matrix, while A times B gave us a 2 times 2 matrix. Clearly, they're very different. A matrix, this very simple table of numbers, can do much more than it first appears. Beyond just storing numbers, the real power of a matrix lies in performing linear transformations. And the key mathematical tool behind these transformations is matrix multiplication. For example, when we multiply a matrix by a vector, we're actually applying a certain geometric transformation to that vector. A 2 by 2 matrix is typically used for operations like scaling, rotation, reflection, projection, and shearing in 2-dimensional space. In the multiplication AX equals Y, if A is a 2 by 2 matrix, then the input X vector is a 2 by 1 vector, and the output Y is also a 2 by 1 vector. In terms of matrix shapes, when we do 2 times 2 times 2 times 1, the middle 2's cancel out. The result is a 2 times 1 shape. According to the rules of matrix multiplication, the number of columns in matrix A must match the number of rows in vector X, and the number of rows in matrix A becomes the number of rows in vector Y. Geometrically, the 2D column vector X represents a point in the 2D plane. It's also a vector starting from the origin and pointing to x1, x2. Similarly, the 2D column vector Y is another point on the 2D plane. It's also a vector. Let's start by looking at two special vectors, E1 and E2. They're standard orthonormal basis vectors. E1 points along the positive x-axis and E2 points along the positive y-axis. Suppose we have a 2 by 2 matrix A. Multiplying A by E1 is equivalent picking out the first column of matrix A. The unit vector E1 is transformed into 2, 1 transposed. Similarly, multiplying A by E2 picks out the second column of matrix A. The unit vector E2 is transformed into 1, 2 transpose. You'll also notice that the unit square grid becomes a parallelogram grid, and its area is 3, which turns out to be the determinant of matrix A, a topic we'll dive into very soon. As 3 by 3 matrix, it turns everything into 3-dimensional space, allowing for even more complex geometric transformations in 3D space. In the RGB color space, the vector E1 represents pure red, E2 represents pure green, and E3 represents pure blue. Suppose we're given a diagonal matrix. Multiplying A by E1 scales E1 by a factor of 2. Similarly, A times E2 scales E2 by 2, A times E3 scales E3 by 2 as well. As a result, the unit cube stretches into a much bigger cube, and its volume grows from 1 to 8, and 8 is the determinant of our 3 by 3 matrix A. There are plenty more examples of matrix multiplication and geometric transformations to explore in this chapter. Please refer to the GitHub uploads. Now let's explore a few fascinating properties of matrix multiplication. When multiple matrices are multiplied in sequence, it's just like applying a series of geometric transformations, one after another. On the screen, matrix C scales x-axis by 1/2 and stretches y-axis by a factor of 2. Matrix B represents a shear transformation along the horizontal axis. Matrix A corresponds to a 90-degree counterclockwise rotation around the origin. So the product A times B times C times the column vector x means first scale the x vector with C, then shear with B, then rotate with A. Please take note, the order of operations goes from right to left. Of course, we can also compute the product A times B times C as a single matrix, then apply that combined transformation to vector x. In that case, matrix multiplication A times B times C represents a composite geometric operation, everything done in one shot. Now consider a single matrix A. On screen, A times vector x gives us vector y. To understand this matrix multiplication, we can decompose this transformation into a sequence of familiar ones. Simply put, matrix decomposition breaks a matrix down into a product of simpler matrices. You can think of it as the reverse of matrix multiplication. For example, matrix A might be decomposed as rotation, scaling, then rotation. This is essentially eigenvalue decomposition, an important idea we'll explore later in the series. Or we might decompose matrix A as shear, scale, then shear. This type of decomposition is called LDL decomposition. Even if both A times B and B times A exist, in general, A times B is not equal to B times A. Sometimes, A times B and B times A don't even have the same shape. Even when they do have the same shape, they might still represent completely different transformations. Let's say A is a scaling matrix and B is a shear. Then A times B times vector x means shear first, then scale. But B times A times vector x means scale first, then shear. Clearly, these result in different geometric effects. But there are some special cases where A times B does equal B times A. If both A and B are 2 times 2 scaling matrices, then the order doesn't matter. The final result is exactly the same. Or if matrix A and B are both rotations around the origin in the plane, then once again, the order doesn't matter. The product A and B equals the product B and A.